Boom. Hello and welcome back to Calculus 2. This is chapter 11. I don't have 11.1, 11.2, 11.3, it's just chapter 11. So chapter 11 technically consists of two things. Lecture number 1, power series in general. Lecture number 2, particular type of power series called Taylor series. And Taylor series would have a special case which we'll call Maclaurin series, and that's it. Now, the book breaks this into 4 sections for unknown reason, where sections 1 and 3 and then sessions 2 and 4 actually work together. So, we are going to start talking about power series first in general, and then we're going to take a look at Taylor series either maybe even by the end of the class, but most likely next time. So power series would look something like this. Summation of Cn x to the n from, let's say, 0 to infinity. Why is this called a power series? Because there is a power over here on the variable x. These guys are equivalent of functions in the world of series. So what were the series before? They were just numbers. So if you're trying to make these connections, sequence is just a list of numbers. Series is the sum of the numbers, so you're adding numbers. And now power series would be functions of that realm. Now, what this is over here is just a polynomial. C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 plus ... going to infinity. So that's what the power series is. I get to box this and just say power series. What do you have on the right hand side? What is this? Isn't it just a polynomial?
Yeah, it's just a very big part.
Do you see that if you just take these 3 terms, you have ax squared plus bx plus c, a regular quadratic from your algebra 1, right? Do you see that if you just take these 2, first one you have mx plus b, linear line. Here's your mx plus b, right? So all this is one big polynomial. This side is a polynomial. Now, do we need this to be a polynomial? Are there different series? Sure. Power series are power series, then you have Fourier series, they will have trig inside. Lorentz series will have complex numbers and functions inside. Yeah, it's all fun, right? So you have different flavors of these guys. We are focusing on a polynomial one, and they're really cool. So now, power series can be centered at a number a on x-axis. So a equals 3. Power series centered at 3. So power series centered at x equals a. Summation Cn x minus a to the n. We didn't do much. So this is going to be C0 plus C1 x minus a plus C2 x minus a squared plus c3x minus a cubed plus 3 dots going forever. So these can be centered at a value. Now we'll see why we need them, right? Now let's take a look at these approximations. You already know the first two-term approximation because you took Calc 1 and you learned linearization in Calc 1. Calc 1. What you learned in Calc 1 is L of x is equal to f of a minus f prime of a times x minus a. So now I want to ask you, does that fit? Yeah, it does. Fits right there. So you already know a two-term approximation to a function, and what we are now going to do is three-term approximation, four-term approximation, five-term approximation for a function, because more you do, the better approximation for a function. Now, why were we doing these approximations? Because we didn't want to calculate square root of 15.1. We wanted to calculate 15.1 in a linear function and make it easy. That's what we did. So now our job is to learn a formula which will give you these constants C0, C1, C2, C3. Now this always stays x minus a to the power, depending which term you're at. And in Calc 2 now, we are going to learn that our Cn is given as the nth derivative calculated at a divided by n factorial. Now,
what is the f to the n power?
that's what I'm about to say.
Oh, okay.
This notation is the nth derivative.
Oh.
So the notation from Calc 1, the 0th derivative is equal to the function. First derivative is a prime, second derivative is 2 primes, third derivative is 3 primes, fourth derivative is a 4 in parentheses, fifth derivative is a 5 in parentheses. This is the notation that you were supposed to learn and know from Calc 1. So now, when I say f in parentheses n, that's not f squared or f cubed, that's the derivative, nth derivative. So with parentheses is the order of the derivative, without parentheses is just f squared or f cubed or whatever, right? So f to the n is not the same as f to the parentheses n. This one is exponents and this one is derivatives. If you don't know this as a notation, write it now so you know it for the, you guys are prepping for DiffyQ, so gotta know that. So if n is equal to 3, 1 on the left is just f cubed, 1 on the right would be third derivative of f. So if n is 3. This is not the same. Not the same. So make sure you have this crossed out. Okay, great.
What's the a?
A is the value at which we are computing. So I haven't explained that yet.
Oh.
So we'll get there. Now, I'm sorry? No, it's just a central location. Back to Calc 1. What is the square root of 15.1? Now, when I draw the graph for a square root, somewhere over here I'm going to have my 15.1. And whatever the value is for the y would be the answer for this. But don't have a calculator really, so I can't compute it. So we do the next best thing. I move over to 16 and I draw a tangent line. Calculate the tangent line. Now, if I go from 15 up, 15.1, observe that the y value, you can't even see it. Observe that the y value of the function, which is the true value, and the y value that you would get from the tangent line, they're close. So, why don't I just find the tangent line and then compute 15.1 in the tangent line, because I'm just doing basic math at that point. And that's the idea of the linearization. So L of x from Calc 1 is the function computed at 16 minus the derivative computed at 16, and then x minus 16. What's your function? Your function is square root of x, because you are calculating square root of 15.1, which means that your f prime of x is 1 over 2 root x. So now, your tangent line, which we write as a linearization, is square root of 16 minus 1 over 2 root 16 times x minus 16. This is 4 minus 1 over 8, and then x minus 16. This is distribute, negative 1 over 8x, and then 16 and a negative becomes a positive, so I have plus 4 plus 2. So L of x is equal to negative 1 over 8x plus 6. Bueno? So this is my tangent line. So now, square root of 15.1 is approximately equal to L of 15.1, and computing negative 1 over 8 times 15.1 plus 6 is a joke in comparison to computing the square root, which you actually can't compute. So now, you do this simple calculation, and you do it by going 15.1 divided by 8 plus, sorry, that's the answer, and then minus, and then the 6. So the answer is 4.1125. I'll put it here, 4.1125. Now, calculator value for square root of 15.1. Square root of 15.1. I did something real.
4 can't be right, it's too big. It has to be less than 4. Square root of 15.1 has to be less than 4.
Yeah, I typed something wrong.
Yeah.
It's 3.86.
15.1, I have 3.8858.
Like I said,
Yeah.
3.86.
Yeah, I see that it's.
8.86.
Well, what did I do wrong?
8.86.
Square root is 14, it's 8, then this one, so 4 So 1/8, and then copy the 4, and then half of 16 is 8, and then that's plus 2, and that's plus 6. So,
This is how I felt when the answer was 46 and not 55.
So what?
On the test we just did.
Okay.
With the square root of u and all that. The answer was 55. I think so too.
Yeah, you can play with that. Which one? What number?
Simpsons and
Oh, that one?
See, he knows how I'm feeling. You put like 28, yeah, you know something?
I got it.
What did you get? Simpsons, that was over there.
what do I have wrong? Come on.
I got a 40-something.
Oh,
It's
it's plus.
No, I got a
No, the formula over here. Holy nightmare. That's a plus. That's a plus. That's a plus.
You got a 46? You got it right.
Yeah. It's a plus. So it's a plus. Plus 6. No. Plus 2. So 15.1 divided by 8 plus 2. Holy nightmare, there we go. 3.8875 in comparison to 3.8859. So you even got the cents, okay. And we haven't computed anything using the root. So now, looking at this calculation, question is, can we do better? And the answer is yes, we can do better if we go to the higher order approximation, and that higher order approximation right now will be actually f of a plus f prime of a times x minus a, and then we add another term, f double prime computed at a divided by 2 factorial x minus a squared. This formula is adding an extra term, and that extra term is going to take care of these differences here and make it even better. It's not going to give you exact, but it's going to do better. Generally, you need to do 3 or 4 terms to have a very good approximation in general. So you can try this calculation and you will see. Now, hello physics. How many times in physics have you heard, let's not compute this, let's just replace sine x with x for small angles? It's rooted in this. So when you take physics, they will say, replace sine x with x for small angles. So that's something that they say in physics. It's okay. Is it okay? Yes, it is. Can we do better than that? Sure we can. Let's take a look at this particular calculation. So if I have my function f of x to be sine x, then what can I get out of this? And I want to say center at x equals 0. So that means your a is 0. All right. So I need few derivatives. F prime is cosine x. F double prime is negative sine x. F triple prime is going to be negative cosine x. And let's do the fourth derivative. That will give us sine x back. in loops. So what is my approximation for sine x using these polynomials and things? So I have f of a plus f prime of a x minus a. I have to go 4 derivatives now. Plus f double prime at a divided by 2 factorial x minus a squared plus f triple prime calculated a over 3 factorial x minus a cubed, and finally f fourth derivative calculated at a divided by 4 factorial x minus a to the fourth. So this is a 5-term approximation because I have original function plus 4 derivatives, right? And now all I need to do is to compute this. So sine x is approximated. I should have said approximated, not equal. There we go, approximated. It's a squiggly equal sign. I have sine of a, that's sine of 0, plus the first derivative is cosine computed at 0, and then I have x minus 0, plus negative sine computed at 0, that's the second derivative, divided by 2, x minus 0 squared, plus the next term is plus. So next term is negative cosine computed at 0 divided by 3 factorial is 6. X minus 0 cubed, and finally plus the sine of, I should have done it one more derivative, sine of 0 divided by, this is now 4 factorial, which is 24, x minus 0 to the 4th. What's sine of 0? So all of the terms that have sine 0 die. This term is 0, this term is 0, and this term is 0 because they all have sines. Look what my sine x is approximated by. It's approximated by, what's cosine of 0? 1 times x. So this whole term is just x. Do we all agree? What else survives? What's cosine of 0? So negative 1 over 6. So minus x cubed over 6, right? I can replace sine x with x minus x cubed over 6. I can replace trigonometric function by polynomial. If you are not fascinated by this, change your majors. Like all of them, quick. Because this means no more exponential functions, no more logarithmic functions, no more trig functions, just polynomials. And now, what's the conclusion of why would we have something like this? Well, how easy is to differentiate and integrate polynomials? Easier than everything else, right?
Yeah.
Well, not e to the x, but still. So now, we have a lot of time, so hold on. We're not nearly done. What I'm doing now is I'm switching my screen to Desmos because I'm going to do some graphing which you guys have to see. Actually, I should do that here, so it can stay as a part of a video. Now this is going to be extremely important. We found out that my sine x graph can be replaced by x minus x cubed over 6. There we go. Let me zoom in. Red line is your sign, blue line is your approximation. Now, let me now just really quick, hey, don't do that. Let me just quickly go back over here and completely erase this. Do you see that the blue line and the red line match for some time? So how far do they match? Well, do we know that this is where the pi's are? Negative pi and positive pi? We know that, right? Great. So at the peak of red is going to be pi over 2. Halfway through, about 7 point something, like half of 1.5 is going to be 0.7 something. 0.7 something is your pi over 4. And then more in pi over 3. Oh, pi over 6, sorry. Pi over 6. From negative pi over 6 to positive pi over 6, that's 30 degrees into positive and 30 degrees into a negative. Don't these match? So does it now make sense when in physics they say you can replace sine x with just x for small angles? Right? For small angles. Now, without touching this, I am going to add this extra term, minus x cubed, me too, divided by 6. Do you see now that these two functions are together longer? So now I can include maybe even all the way to pi over 3 on both sides, because the functions match nicer, right? Now, yes?
Is there any deviation at all, or are they exactly the same?
At the beginning, they are exactly the same. And then deviation starts when you start seeing them apart.
Okay.
Now,
So wouldn't that be the tangent line?
it's not a tangent line because it starts curving on top. Tangent line is the linear line, just the first term approximation, first two term approximation.
Yeah, the x.
But now this one is giving you x squared and x cubed and x to the fourth. So this can be infinite. So it's not a tangent. Tangent line is a linear line. This approximation is gonna bend itself. And look, I'm adding another term. Plus x to the 5 divided by 120. You see that it fits even better? Actually, you know what? Let's just do this. So, can I? Nice. Control C. All right, we can do that. Then Control V. Yes. I go with X in front, and then I kill off the. I kill off this one. There we go. And then I will also put just X. Excellent. Red line is your target. Do you see that if you go from the purple to the green to the blue, it's getting better. It's getting better. Can I do even better than this? I believe that the next one would be 7 factorial 720, right?
Yes, no. 6, 7, yes, 740.
740?
7 is 120, 840. Y factorial is 126.
Well, then you need to do times 6 times 7.
Yeah, 42 is big. 41.
It's something. X to the
5020.
5020? 5040. 5040. Look at the black line, guys. You see that the black line did even better than the. So your goal is to approximate. So do you guys see that I can use the black line and almost go throughout the entire period of sine? Right? Entire period of sine. It's not really fitting at the end. There is some deviation, right? You can see some deviation at the end. But look at this, right? You can see when they start checking out in terms of convergence. So they converge to the function. They converge to the function, and the more terms you calculate in this approximation using these derivatives, the more terms you have, the more agreement you're going to have between your polynomial and whatever squiggle you have on the other end. They're going to line up with the exponential. They're going to line up with the logarithmic. They're going to line up with your hyperbolic functions and trig functions. And technically what this is doing is taking all of those functions out of commission. Now, as you can see, it's not entire domain. They start diverging from each other. So if you are using these approximations, you have to be very careful where you are using, which is what this A business is. You have to center your approximation around the point of interest. Now we centered our approximation at 0, so sine of 0, and then the approximation at 0. I can do my approximation, let's say at pi, and if I calculate pi, my A would be pi, and I would calculate everything for sine again using not 0 but pi, and they would perfectly match here and start diverging by the 0 and by 2 pi. So that's what the centering means, that A. You asked me already. So if I am to center power series, in this particular case, at let's say pi over 2, then the red line and all of the other lines would perfectly match right there and start diverging to the left and to the right. But in this region, around pi over 2, they would match perfectly for some amount of left and right interval. So when I think of power series, I don't think power series 2 and 3, which is actually what it is. I say power series because really, come on, you are taking some stuff that it's exponential function and you turn it into a polynomial. You're taking a trigonometric function, you turn it into a polynomial. Hyperbolic function, you turn it into a polynomial. And when you have those, you can do very easy calculus because you are transforming your whatever you have into a polynomial, and then you're just integrating and differentiating and taking the limit of a polynomial, and that's a joke. Now, we will all agree that if you have integrals and derivatives of e to the x, that's easier than polynomial, but the rest of the stuff is not. So this is extremely, extremely useful, and it helps us a lot in many examples. Now, we need to build up to the calculus use, and we need to define this as power series, Taylor series, and so on. But before we get there, we need to understand more about power series. So let's go back to our notes, and we'll come back to these calculations. You can go and calculate a whole bunch of this other stuff. You can try other functions. They all do the same way. Now, guys, what I'm going to have now is very important. So, what we have next is convergence of power series. And for the convergence of power series, you have seen the colorful example of what this means. Convergence means that these graphs are on top of each other and they are having the same values as y's. And then they start diverging. From the red line. And then the more terms you have, the convergence sticks around for longer. The idea is that if you do infinitely many terms, you will have exact function, except you're writing it a polynomial. The trade-off, obviously, is that your polynomial has infinitely many terms. So, yeah, that's bad. But when you are doing finite calculations, you definitely want to do them in a polynomial because it's easier, right? So now, why is the convergence of these power series important? Well, you know your tests, right, from chapter 10. And we are going to take a look at, let's say, geometric series test. You know that the number r, if the r is between -1 and 1, converges. If it's 1 or more, diverges. You memorize that on the sheet. Now let me ask you a question about power series. Let's say you have 0 to infinity, and let's say you have x over 3 to the n. X over 3 to the n. What numbers can this x take on? What numbers can this x take on? Any, which is y is a variable. Can it be -7? Yes. Can it be 1.3? Sure. Can it be square root of 500? Sure, right? So x can take on any number. But what about convergence or divergence of this series as this takes different values? If x is equal to 1, is it the same as if x is equal to 5? What can you tell me about this power series if x is 1? Why? You are correct. Why? Ah, nice. So, immediately figure it out. If you have x equals 1, if you have x equals 1, your r is 1/3. That's less than 1 converges by geometric. Because, guys, this is called power series if I have x. Just like this is called an equation if I have x. Right? It's a function. As soon as I replace this by a value, it becomes a 4. It becomes a number. So, this is a power series. But if I pick a value for x, it becomes geometric series. And geometric series has the r smaller or larger than 1. So, do you get to say that the power series converges? No. Because certain x's are going to make it converge, and other x's going to make it diverge. It depends on the value of x. Right? So, in this particular example, but I already figured it out that if your x is between a -3 and 3, power series converges. If it's out of that bound, it diverges, because you will have r's that are outside of the bounds. So what we are interested in is something that is called interval of convergence. Yes?
X is -2. So -2 I get 4, and -3 I get -8. It's going to toggle back and forth with negative and positive. How does that work out?
If x is -2,
Yeah, n is even, I'm going to get a positive number. When n gets to be odd, I get a negative number.
yes, but we don't have to worry about it, because it's convergent by the geometric series.
Still going to be
Because in geometric series you have absolute r less than 1 converges, right? So you can have a positive or negative, it doesn't matter. But I'm going to prove this using the ratio test, so we're getting there. Interval of convergence. Use ratio test. So let's say for this example, I have my an, well, let me write example again. I have my an as x over 3 to the n. I have my an plus 1 as x over 3 n plus 1. We need to do the limit. N goes to infinity. We have an plus 1 divided by an in absolute values. Now these absolute values matter a lot. Limit n goes to infinity of x over 3 to the n plus 1 divided by x over 3 to the n in absolute values. Next, limit n goes to infinity, absolute value of x over 3 times x over 3 to the n times 3 over x to the n when you multiply it up. Or you can leave it and cancel, whatever. These guys are going to cancel. And now, limit has nothing to operate on, because your limit n value goes to infinity, and all you have is x over 3 in absolute value. So, the value is just absolute x over 3. Now, this is the confusing part, but it shouldn't be. What are we looking for? We are looking for the interval of convergence. When is ratio test convergent? When it's less than 1. You get to set this less than 1.
I get it.
You get to set this less than 1 because you want the convergence. You want convergence to be revealed to you. All right? So, you remember when you look for minimum and maximum, you set derivative equal to 0 to reveal x's at which you have min and max. Do we remember that from Calc 1? Right, what do you want now? You want convergence to be revealed. Set it less than 1, because in the test, that's when the convergence happens. And what do you get now? You get algebra 1 equation to solve. Absolute x over 3 less than 1. This means negative 1 less than x over 3 less than 1. This is three-sided inequality, hit everywhere by 3, and this is what Matsal already told us, that the interval of convergence is from negative 3 to 3. What does this mean? This means that any number that you pick from this interval, your power series converges. Any number outside of this interval you pick, it diverges. So this is your interval of convergence, right? So this is interval of convergence. And then another concept that we tie to this is radius of convergence. R equals 3. It's half of the whole thing. Radius of convergence is 3.
Are we going to have to put the radius of convergence? Or
Yes.
just the interval?
They travel in pairs.
So if we were to get a problem like this and we put,
Not if, when.
when we get a problem like
This is guaranteed problem for final exam, 100%.
okay, we're going to put interval of convergence is negative 3 to 3.
Yes,
And we're fine.
R equals 3, yeah.
R equals 3.
Yes, you can leave this, you can have this, it's either or.
Okay, but we have to specify R equals 3.
Yeah.
Okay.
I want to do one more example. I know the class is over 1 minute, but one more example. It's better if you have it.
You don't know much.
Summation of negative 1 to the k, x minus 2 to the k, divided by 4 to the k, 0 to infinity.
That's alternating.
Well, it's a power series.
So it's power alternating.
Yes. when you pick an x and you plug that in there, it becomes alternating series. But with having an x as a variable, it's a power series. And we do not have divisions for power series. So it's a power series if there is an x. Once you have a particular value in mind for that x, then it becomes some kind of series from your sheet, right, of 10 tests. So, what is the interval of convergence? What is the radius of convergence? Those are the questions, and you immediately proceed with the ratio test. So AK is negative 1 to the k, x minus 2 to the k, 4 to the k. AK plus 1 is negative 1, k plus 1, x minus 2, k plus 1, divided by 4, k plus 1. Next, limit k goes to infinity, absolute value, negative 1 to the k plus 1, x minus 2 to the k plus 1, divided by the 4k plus 1, times, flip this one, 4 to the k, so you save a step, negative 1 to the k, x minus 2 to the k, close absolute value. Absolute values are going to kill negative 1 to the k. Make sense? Because that's just providing negative signs, absolute value kills it. So all the terms have to turn out to be positive. Limit k goes to infinity, absolute value, x minus 2 to the k. I peel off this plus 1. Divided by 4 times 4 to the k. I peel plus 1. 4 to the k on the other side. Right, the times. And then I have x minus 2 to the k. Negative 1 died because of the absolute values. Ready to cancel? Sure. Boom, 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 boom. No more k's. Limit, k goes to infinity, has nothing to operate on because all I have is absolute x minus 2 divided by 4. So that's just absolute x minus 2 divided by 4. Again, you want the convergence, you set this less than 1. Right? You want the convergence, it's your job to set it less than 1 because you are looking for all x's that will satisfy this. So the interval will be revealed to you. Look at that, right? So now, what is the meaning of this? The meaning of this is that negative 1 is less than, right? This is hello algebra 1 or algebra 2, whatever the hell you learned this. It becomes a triple inequality. And, no absolute values. You write the triple to kill the absolute values. Times 4 everywhere. So becomes negative 4 less than x minus 2 less than 4. And then you add 2 everywhere to get x alone. That's your job. And you have negative 2 less than x less than 6. Hello interval, right? Any number that you pick from this range, you are going to get a convergent alternating series. Any number you pick outside of this range, you are going to get a divergent one. Right? What's my radius of convergence? 4. Because, guys, I have 2 units this way. I have 6 units this way. Together, that's 8 units, right? Because this is 2 units, this is 6 units, that's 8 units together. Cut that in half. Right? So radius is 4. Now, at what value is this happening? At what value is this happening? Huh? 2. Are you surprised? Are you surprised that it's happening at 2?
Oh, right.
What did the problem say?
Yeah.
I have a power series centered at 2.
Yeah.
Well, do you have a power series centered at 2? Sure you do. If your interval is from negative 2 to 6, the dead center of that interval is at 2. So that's your checkpoint at the end of the problem. You make sure that you have your interval, you find the center of that interval, and that center, location of that center has to match your center above. Now, let me ask you, where is this one centered? At 0, because it's x minus 0, right? What's in the center of the interval negative 3 to 3? 0, right? So guys, what we did tonight is, for power series, is 11.1, 11.2, and a little bit of 11.3. We'll be done with this chapter, and we'll do many more examples on Tuesday. And we'll push on in Calc 3 prep. We'll have a review for the final on Thursday. We are left with another 5 hours of Calc 2, so we'll manage. I'll see you all next week. Ciao.